Under the theory of repulsion field, how does the Sun work? Under the theory of repulsion field, it is believed that, if pure neutron matter, the matter that is made of 118 chemical elements and can be found everywhere on the Earth, is put in conditions of extremely high temperatures and pressures, like those at the centers of black holes, stars, including the Sun, such pure neutron matter will be converted into rich neutron matter. And the reverse also holds true. If pressures and temperatures of a rich neutron matter body is lowered, for example, if it is no longer surrounded by pure neutron matter for some reason, such rich neutron matter will be converted back into pure neutron matter. The conversion from pure neutron matter to rich neutron matter does not release energy, but the conversion from rich neutron matter to pure neutron matter releases massive amount of energy. This is the way that the Sun and other stars generate energy and shine. More specifically, there is a continuous back and forth conversion between rich neutron matter and pure neutron matter in the inner parts of all shining stars, for example, the Sun. The energy generated by the conversion from rich neutron matter into pure neutron matter, in turn, makes the stars shine. In any case, rich neutron matter always act as an explosive. This special explosive explodes below the areas around the equators of the stars. And the explosions release massive amount of energy and make the stars shine. The second important point of the theory of repulsion field is that bodies of rich neutron matter produces repulsion field in the surroundings, and this repulsion field, in turn, repel the surrounding bodies of rich neutron matter. The repulsion field is similar to the gravitational field in its nature, but it works against the gravitational field. Gravitational field is produced by pure neutron matter and it attracts the surrounding bodies of pure neutron matter. Meanwhile, repulsion field is produced by bodies of rich neutron matter and it repels the surrounding bodies of rich neutron matter. Gravitational field does not interact with bodies of rich neutron matter. The reverse also holds true. Repulsion field does not interact with bodies of pure neutron matter. No instrument nor laboratory apparatus, that is made of pure neutron matter, can measure any property of rich neutron matter, even the mass of rich neutron matter bodies. So, what can be concluded from the theory of repulsion field is that, there is a significant amount of rich neutron matter, which is called the body of solar rich neutron matter, at the core of the Sun. This body of solar rich neutron matter is covered by a quite thick layer of pure neutron matter on the surface of the Sun. Because of this thick layer of solar pure neutron matter, it is impossible to observe the body of solar rich neutron matter. This thick layer of solar pure neutron matter helps maintain the extremely high pressure around the body of solar rich neutron matter, and protect this body of solar rich neutron matter from explosion. If the Sun did not spin, the body of solar rich neutron matter would remain unchanged. There would be no back and forth conversion between solar pure neutron matter and solar rich neutron matter. There would be also no massive amount of energy released from the Sun, and finally, the Sun would be just a small black hole and it would not shine. However, the fact is that the Sun spins around its own axis. The solar spin helps bring the body of solar rich neutron matter closer to the solar surface, in the region around the solar equator, turn the solar rich neutron matter into the solar pure neutron matter, cause massive rich neutron matter explosions, at and around the solar equator. These massive rich neutron matter explosions produce massive amount of energy and make the Sun shine. The next part of this video will explain in more details, how the solar spin create the back and forth conversion between solar rich neutron matter and solar pure neutron matter. It makes sense that when a spherical body, like the Sun, spins around its own axis, this spherical body will turn into a spheroidal body with its two poles being partly flattened, as illustrated in this video clip. If the appearance of the Sun is a spheroid, the body of solar rich neutron matter in the inner part of the Sun therefore also approach a spheroid. More specifically, the line segment CD is longer than the line segment AB in this image. What can be concluded from the spheroidal body of solar rich neutron matter is that, the body of solar rich neutron matter exerts a greater repulsion force on bodies of rich neutron matter near the solar equator than the repulsion force that it exerts on bodies of rich neutron matter near the two solar poles. So, what can be concluded from this is that solar rich neutron matter always moves from the solar core to the solar equator. Meanwhile, the partly flattened solar poles facilitate the collection of the solar pure neutron matter from the solar equator, and gather it up at the two solar poles. This results in a thinner layer of the solar pure neutron matter, at and around the solar equator. And this, in turn, lowers the pressure of the solar-rich neutron matter at and around the solar equator. Finally, the lowered pressure facilitates the conversion from solar-rich neutron matter to solar-poor neutron matter. So, what can be concluded from this is that, below the surface at and around the solar equator, solar-rich neutron matter explodes, and then, is converted into poor neutron matter because the pressure is lowered, and produces massive amount of energy there. Similarly, below the surface of the two solar poles, where poor neutron matter gathers up and creates extremely high pressure there, solar poor neutron matter is converted into rich neutron matter. Solar matter, including both solar poor neutron matter and solar rich neutron matter, circulates from the center of the Sun, towards the solar equator, then towards the two solar poles, and finally back to the center of the Sun. As said previously, the conversion from rich neutron matter to poor neutron matter liberates massive amount of energy, coming from rich neutron matter explosions. Because these rich neutron matter explosions occur at and around the solar equator, but not at the two solar poles, this explains why the solar equator is hotter than the solar poles. The difference of temperature between the solar equator and the two solar poles is what has been confirmed. If such rich neutron matter explosions are strong enough in magnitude, a part of solar-rich neutron matter will escape from the Sun, and then, be driven into the space, and produce what can be referred to as strong solar wind, or just solar wind for short. Initially, solar winds are accelerated into the space by repulsion force that is exerted by the body of the solar-rich neutron matter. This phase is called rich neutron phase of solar wind. Later on, the solar winds, which is initially made of rich neutron matter, are converted back into poor neutron matter, the matter that can be found everywhere on the Earth. This phase is called poor neutron phase of solar wind. This poor neutron matter is then decelerated by the gravitational force exerted by the solar poor neutron matter. This poor neutron matter ends up at either planets or asteroid belts. What can be concluded from this is that planets and asteroid belts all develop from solar winds. They all are built up by solar winds. However, there is an important question left unanswered. Why are the four innermost planets, which are Mercury, Venus, the Earth, and Mars, are terrestrial planets, but the four outermost planets, which are Jupiter, Saturn, Uranus, and Neptune, are gaseous planets? This question is answered as follows. After the solar wind leaves the Sun, it takes less time for the solar-rich neutron matter, that comes along with solar winds, to be converted back into heavy chemical elements like iron, nickel, etc. These heavy chemical elements then gather up in the innermost planets, which are Mercury, Venus, the Earth, and Mars. This explains why these four innermost planets are terrestrial planets. Meanwhile, after the solar wind leaves the Sun, it takes more time for the solar-rich neutron matter, that comes along with the solar wind, to be converted back into lighter chemical elements like hydrogen, nitrogen, oxygen, etc. Because the rich neutron matter coming along with the solar winds exists for longer time, after the solar wind leaves the Sun, this solar wind has more time to accelerate and is able to attain high enough velocity to reach the outermost planets. In other words, these lighter chemical elements, which stem from this sort of rich neutron matter, end up at the four outermost planets, which are Jupiter, Saturn, Uranus, and Neptune. And this explains why these four outermost planets are all gaseous planets. How about solar winds that emerge from the solar surface, but are unable to escape from the Sun, hereafter referred to as weak solar wind? The fact is that weak solar winds always fall back to the nearest pole of the Sun, assuming that the solar atmosphere does not interact with the solar winds. In other words, if weak solar winds occurring somewhere in the northern hemisphere of the Sun, they will tend to fall back towards the north pole of the Sun. The reverse also holds true, weak solar winds occurring somewhere in the southern hemisphere of the Sun tend to fall back towards the south pole of the Sun. How is this phenomenon explained? This question is mainly because of the uneven distribution of matter inside the Sun. What we can see from this image is that solar-rich neutron matter mainly gathers up around the solar equator plane. Meanwhile, solar-poor neutron matter mainly gathers up around the two solar poles. Similarly to strong solar winds, weak solar winds can be divided into two phases. The first phase is the rich neutron phase and the second phase is the poor neutron phase. Let's take the solar wind inside this blinking red circle for an example. During the first phase, weak solar winds contain mainly rich neutron matter and is accelerated into the space by the repulsion force exerted by rich neutron matter around the equator plane. During the second phase, because rich neutron matter of the weak solar wind has been converted into poor neutron matter, it is therefore attracted by the body of poor neutron matter gathering around the nearest solar pole. This explains why weak solar winds occurring somewhere in the northern solar hemisphere fall back towards the solar north pole, and weak solar winds occurring somewhere in the southern solar hemisphere fall back towards the solar south pole. The final important note of the Sun is the two big polar solar cyclones. As previously said in this video, there exist continuous flows of poor neutron matter on the surface of the Sun from the solar equator to the two solar poles. Because the Sun is spinning around its own axis and because of the law of momentum conservation, it makes sense that these continuous flows of solar poor neutron matter, from the solar equator to the two solar poles, create the two polar solar cyclones, which is called the North Pole solar cyclone and the South Pole solar cyclone. And these two polar solar cyclones revolve in the same direction as the spinning direction of the Sun, if they are observed from above. In summary, the theory of repulsion field helps answer the following unanswered questions about the Sun, and also the solar system. 1. Where does solar energy come from? The short answer to this question is that solar energy comes from the conversion from solar-rich neutron matter to solar-poor neutron matter. 2. Where do solar winds, planets, asteroid belts come from? The short answer to this question is that solar winds erupt from solar surface, at and around the solar equator, where the layer of solar-poor neutron matter is thinner than that of the other areas of the Sun. Solar winds last in two phases. During the first phase, or the rich neutron phase, solar winds are accelerated into the space by repulsion force exerted by the body of solar-rich neutron matter. During the second phase, or the poor neutron phase, solar winds are decelerated by the gravitational force exerted by the body of solar-poor neutron matter. Finally, poor neutron matter from solar winds make up planets and asteroid belts. 3. Why do weak solar winds fall back to the nearest solar poles, but not to the place where they have erupted from? The answer to this question is because the two solar poles are the two hubs of poor neutron matter. During the second phase of solar wind, poor neutron matter is converted from rich neutron matter and is attracted by the nearest hub of solar poor neutron matter. That is why weak solar winds fall back to the nearest solar pole. 4. How are polar solar cyclones developed? The answer to this question is because solar poor neutron matter, which is converted from solar-rich neutron matter, at and around the solar equator, is attracted by the nearest hub of poor neutron matter at the solar poles. The law of momentum conservation turns these inwards flows of poor neutron matter into polar solar cyclones. Thank you for watching.